Welcome everyone to another breaking news. Intel just announced that they are finally planning to remove very legacy 30 years. You heard it here previously. I made detailed videos about CISC versus RISC, various instruction set architectures such as x86, ARM, RISC-V, Spark PowerPC and such, including a retrospective of 20 years AMD 64, what Intel copied for Intel's extended memory EMT64 thing. Intel finally, and I said it before also in ARM, usually recurrently say x86 way too complex, convoluted, and ARM, RISC and so on, so much higher performance, energy efficient to implement in ASICs. So what did they plan to remove is what they carried forward since the introduction of the Intel 8086 in 1978, the original 16-bit real mode that I wonder for a very long time that even I, with all my vintage and retro here, SG Octane and so on, PS3, that is only a decade or two old and not as complex. So Intel dragged around support for executing original 8086 16-bit 64K segmented real mode, as you see here, and apparently all the latest and greatest Core i 13th gens and stuff still, to my surprise, boot with initializing, probably, as least Intel says so, here initializing to the reset vector and executing the bootstrap code from there. Truth be told, Intel could long have got away with that, in my opinion, probably as long as 20 years, as long as AMD 64. Basically, AMD could have long gone away with this because the BIOS code, it's not like you boot DOS or the BIOS had to be 16-bit, although probably with all the vintage and retro stuff, probably as lazy as the Windows boot stuff was, unfortunately due to Microsoft's Win-DOS, quick and dirty garage operating system. Unfortunately, probably it really was necessary 20 years ago. But certainly since 10 years or so, EFI, at least booting 32-bit, it's technically not needed, and it's not like you boot DOS in latest and greatest epic thread-ripping CPUs anyway. So what is this all about? I made a dedicated video, so you probably want to watch that. But the quick summary, the tried in 1 minute summary is 8086 had 16-bit execution with 64K segments that were addressed on 16K offsets, so you could basically overlap the segments in 16K granularity. Then Intel tried the first protected mode with the 286 that was highly unsuccessful, barely anyone used it. It was still 16-bit, right? 1 megabyte or so, got to be enough for everyone, and 64K segments. But also it was really hard to exit it, so Intel thought protected mode is so amazing, which of course it is, just not on the 286, that you could barely get out of it, right? There was, you basically had to reset the CPU, and then some BIOSes had some hacks of quicker keyboard controller, whatever, memory address store reset, and even that hackery was still mighty slow, right? So nearly nobody used the 286 protected mode. The real protected mode that we are still using kinda sorta today, at least when you're booting 32-bit operating systems, was introduced with the 386, 32-bit registers, addresses, 4 GB should be enough for everyone. 4K segments, later huge, not sure if the 386, but later processors, Pentium Pro, so supported larger page sizes of 1 or 2 megabyte, huge pages or what for performance of databases and other large mappings. And the Pentium Pro extended that with a physical address space extension PAE to 36-bit, I believe, that you could not use at once because it still was a 32-bit processor, but at least similar to the 8086 segmented stuff of some database applications in user space could use other parts of your 36 bits of physical address extended memory. That is already convoluted enough, plus of course MMX and all the other architectural extensions, but it was basically Intel wanted to abandon that and had, together with Hewlett Packard, their IA Intanium Titanium IA64, totally incompatible, completely architecture from scratch, because x80, even Intel 20 years ago, 25 years ago, considered x86 so complex, convoluted and low performance that they wanted to do something better, but that totally flopped because probably backward compatibility and this stuff was also too complex for compilers at the time to optimize anyway. So what we use today is actually AMD's, previous video, AMD's AMD64 x86-64 extension that is known not by Intel, that Intel abandoned x86 25 years ago. The successful extension came from AMD, which hacked the 32-bit or the 16-bit 32-bit further extended to 64-bit 20 years ago with the first Opteron and then Athlon 64. And Intel, of course, seeing that people wanted to use binary compatible stuff on Windows and so on, copied AMD's extension and named it EMT64 and still calls it Intel, they call it here 16-bit, whatever, somewhere. Yeah, ironically, Intel can't even be honest enough and call it AMD. So 2004, 64-bit Intel architecture, it's like, yeah, you copied AMD stuff. So AMD released it in like around 2000 as a technical paper and overview for OS vendors like Linux and I heard Microsoft so to adapt. And it later then, 2 years later, so released the first CPU, and Intel, of course, later, when Titanium failed. So with all these extensions, there's of course silicon debt. That means they need to implement support for this. Well, until now they wanted to support this for backward compatibility that nearly nobody used, right? It's not like you boot Windows, like even Windows 95. Okay, no, that was wrong. Like Windows NT based. Windows 95 also would boot through DOS and 16-bit actually. So it's not like you would boot Windows 95, 98 ME or stuff. Anyway, and ironically, support, like with all this legacy that is living in your ASIC, in Intel's application-specific integrated circuit, and taking some amount of die area, be it whatever, so many square millimeter of whatever, of course multiplied with all the cores and stuff, and that is a problem, right? Having the already super complex x86 with this complexity, yes, it's not that much complexity, but it's adding up, right? And the decoder is already the bottleneck, and the decoder, the x86 instruction decoder, variable length instruction of 1 to 32 or so bytes, has to be implemented and taken care of this kind of legacy. So complicating high performance throughput, like 6-8 wide decoding and issuing of instructions, and basically consuming silicon areas that is nearly never used, even in the boot process anymore. The irony is that what many people didn't know is that this infamous A20 gate, which was gating the 20's address line since the 386, I think initially multiplexed with the keyboard controller of all hacky complex x86 things, was removed. So this was, by the way, for backward compatibility. If you're wondering what was that for, this is for having that always zero, so gating the 20's address line, so that because the thing is on an original 886, if you addressed the highest address, which was megabyte, plus the 64K segment size, you had some overlap that was overflowing to the very beginning of the address space. So it addressed 1 megabyte and then some. You could address the first nearly 64, I believe, probably 50. I'm not sure if you could address a full 64-bit or if minus 16K, so that would make it 48K or so, whatever. But as far as I remember, a lot of hacky high performance DOS software used this overflow to address, for example, interrupt vector table or other BIOS or low level and so on stuff, or TSRs and so on. So lots of low level software would fail without the A20 gate on this 386 because without the 820 gate, the memory would no longer overflow to the first zero-based address, beginning of the address base, but would actually address the actual real 1 megabyte and then some. So that is what the short story of the 820 line. So you could already, since 2008, with all the 64 real mode legacy in Intel processors, not directly boot DOS or FreeDOS due to, I mean, maybe there are some FreeDOS hacks, not sure, but at least not the original binary from MS or Quick and Dirty DOS, because the 820 gate was already removed since 2008. And yet Intel kept all the legacy around. I would have long removed it, basically like in probably 2008, because, or like at least 2010 or 12 or so, like basically for, even I would have removed it for 10 years and have some extra 5% or so performance increase since then for improved decoding and using all the logic gates for actual stuff that is used and not stuff that's never used. So what's the outline here is, in this document, they also have a document ironically titled Microsoft Word because, of course, a big mega corporation saves their new ISA document titled Microsoft Word-686 Professionals. But they have, of course, a document here with 46 pages plus or like minus some cover and so on. So 32-ish pages of actual content. And what they're proposing is to remove it, surprise when I remove it, and basically also that means that instead of initializing and resetting, I'm surprised it works like this. I'm not 100% sure. Maybe I should have looked into core boot, Linux BIOS and such stuff, because I thought the platform initialization stuff like AMD's Agesa and what Intel's ME whatever microcode equivalent is, the CPU needs microcode anyway and so on with embedded power and supervision controller there. I'm not even sure if that is accurate, right? We could check this with reading actual core boot. The only problem is like, yeah, good luck reading core boot. It could be that you spend an hour or 4 hours of reviewing core boot code, if this is actually true. But at least Intel claims here that even the latest processors reset to init and reset to 16-bit mode. Not really sure, maybe it is true, maybe it's not, but anyway. And with that removed, they need, of course, define a new initialization and reset vector and state of the CPU so that the state comes not in initialized and reset to 16-bit real mode, but to some 32-bit mode with pages. They also want to remove a little bit more stuff. Actually, do they? So this basically what you see here. So what this means in practice is that you can no longer boot surprise DOS, Windows 3, 95, 98. And with that, depending on how lucky you are, maybe a modern Linux, I'm not sure if that would work by chance. Although a big mega corporation would potentially specify it so that at least current year's Windows and Linux would still boot. Because they want to remove a little bit more than that, so, or a little bit less, I kinda would have also removed full 32-bit support, but that's not what they are doing. So they basically want to remove 16-bit mode and 32-bit mode for, where was, by the way, is this somewhere? Somewhere was here probably. Of course, the benefits are a simplified, streamlined silicon, right? They can focus on current gen high-performance 64-bit speculative execution stuff. They also want to eliminate most of the 3 rings that were barely used. x86, so usually RISC CPUs from the Unix world have only supervisor and user mode. Intel implemented 4 rings that you could theoretically, Intel planned in their original 386 papers, which I studied at the time, that you would have in ring 0 the kernel, and in ring 1 drivers, and in ring 2 other operating system services, like not at the time, but or network stack, or nowadays like Wi-Fi and Bluetooth stack, but and then in ring 3 the user space stuff. But the truth is nobody used them except, yeah, probably OS2, Warp and stuff. So there were some users, but they were really, really rare. I personally tried to use it like that. And with that also eliminating support for Ring 3 I/O port access. So there is a bitmap that the operating system can fill out to allow, like, if a driver like Xorg or so, or similar such stuff on Windows and so on, could directly poke I/O ports. This is an extremely old concept from the 8086, XT and AT. Nowadays we have memory mapped I/O anyway, so that is not a high performance feature like you might have a serial port there, or Sound Blaster, Gravis, ultrasound could be driven in that mode directly. This is not really that much loss because nowadays this feature is extremely rare. You would normally not use it, and for modern hardware you don't need it, right? Modern hardware is memory mapped and not I/O port driven. Also, with that, eliminating string port I/O on x86, 8086, you could use the string repeat instructions to have the CPU loop and output more than one word or byte or word on those I/O ports, which again, rarely used, right? It's not a modern hardware feature and so on. Also, add that eliminating support for local, limiting support for local interrupt controller APIC to use X2 APIC. My previous video, right? I patched this for the Linux kernel because actually, chances are this high performance X2 APIC present in AMD CPUs probably you're not using, because on most hardware BIOSes and terminals it is buggy and the Linux kernel will use it. So unless you're using T2, my Linux distribution, or my patches, chances are you are missing this high performance feature. I probably should send it upstream. Getting rid of legacy 8259 interrupt control support, those that came with the original IBM XT or IBM PC XT and 80 then, and were used until 486, somewhere 486 Pentium local interrupt controller APIC was introduced. Again, an extremely legacy feature. Of course, initially used for everything from disk controller, sound cards, and so on. But nowadays we have PCI interrupts and on modern hardware anyway message signaled interrupts. And so that's certainly like getting rid of, similar to the 820 gate, getting rid of the oldest, the most legacy of the legacy that has no use and so on. And removing some other unused operating system bits. If we take a look here in this longer document, I somewhere should probably not have scrolled so much to here, because here's a more complete list than this marketing slide. So to summarize this, changes to the x86-s, whatever S may be simplified or whatever. In scrolling over, I've not found what this S is. Maybe x86 subset or simplified or whatever you want to call this. If I missed this, and I'll leave in the comments below. So restricting the CPU to be always in paged mode, removing 32-bit ring 0 as well as VM86 mode. Again, VM86 mode is already not supported in long 64-bit mode. So that also means running 30. So this sounds like it's also not supported running 32-bit operating systems. That would mean only running 32-bit user processes in modern operating systems. So you could potentially still run a 32-bit binary on your Linux or Windows system. Removing ring 1 and ring 2, again, barely used, at least not with Linux anyway. Removing 64-bit real and protected modes. I'm actually, that is really funny. I always wondered whether this 286 protected mode would still be supported. I always wanted to try this out. It sounds a little bit like, I mean, this is the craziest of the legacy features, that if today's CPUs would still support 16-bit protected mode, probably should test that someday. I actually have a 286 from the attic of my parents last year. I took actually 286 that, to my surprise, is actually working. So share, like, subscribe, maybe we do some 286 vintage stuff. Not this year because we have a microkernel to write, but maybe another year for more vintage and retro content to come. Removing fixed MTRR, that is memory type range register, that was only ever used for changing the caching modes, right, combining and so on for your video frame buffer. That is also long not used because since the PAE physical address space extension from the Pentium Pro, you could mark this on a per page basis. So like they usually get 4 or 8 entries, and they ironically were all different, like Intel had different than AMD VR and Centaur transmitter and so on, and they were only 4 or 8 depending on the architecture anyway. And again, so nowadays you have much more granular control, not really anything is lost, and modern systems long don't use it anymore. User level I/O, as I mentioned, so that is the user process like x86 I/O ports. So that would only matter if you run a legacy VGA card, S3 or stuff on your Xorg server. Again, nothing. You could still in kernel do probably I/O ports if you needed that for vintage stuff support. ZR0 write-through mode, legacy, so also removing legacy FPU control bits in ZR0. And that sounds that legacy x86, legacy x87 FPU would no longer be supported. Again, a rarely used feature that it's like, does not mix well with high performance AVX, SSE, MMX 3D, not good anyway. Removing ring 3 interrupt control flag support, removing obsolete CR access instructions. You see, they are a little bit like here's some bits, there's some bits, all this grown legacy. When you look into the Intel architecture documents of 1,000, 2,000 pages, always like here's some bits, there's some bit, and so on, of all this, now legacy details. Re-architecturing init SIPI, new mechanisms to switch between 4 and 5 level page tables, remove X-APIC and only support X2 APIC, remove APIC support for 8529 legacy interrupt controller, disabling the NX or CISC call or long mode in the MSR. So that means that no execute would always be enabled, so disabling that, right? Because x86 for the longest time, until I believe AMD, and the NX bit, the no execute bit, as far as I remember, was introduced by AMD with their AMD 64 specification, but comment below if I remember that wrong. NX, of course, meaning no execute, because otherwise there was only in 386 protected mode, there was only read and write or so, and not execute. So execute was always write. Also, did you read write for execute? Actually, we could maybe quickly NX bit x86, something of that sort. It's not like I write this code daily, and of course you run with NX anyway. So there was originally blah blah blah, flat memory. AMD added no execute NX bit in the page table. AMD, as I said, mechanism to control execution per page rather than per whole segment. Right. So previously the whole segment was, and so having a per page control for that. Removing SS and P exceptions, supporting subset of segmentation architecture with the following conditions, restricting the subset to the IDT event delivery base only for FS and GS, because so previously you could have bases also for all the other segment registers, because of course you have multiple segment registers. Because previously the segment registers are a complex legacy of the complex x86, complex and legacy, right? Because of course the 8086 is based on the 8085, which is based on the 8080, which is based on the 8008, which is based on the 4004, something like that. So there's always some legacy. And when you only had 64K segments with the granularity of 16K, of course, you had often, even on an IBM PC, XT80, U286, you often had more than 64K, right? Of course, you had a whole megabyte or later more to address. And the way that worked is that you could have code data extra and F, so you had E and F and G. So you could have multiple segment selectors to various spaces of your freaking 1 megabyte, right? So you, for example, you could have your code at 0, just as an example. You could have your data at 64K and then extra E, F, G segments. So you could at least with this segment selectors, segment registers, address a little bit more of 64 views into your whopping 640K should be enough for everyone. So removing those base and limit for global descriptor, interrupt and TSS. No limit on data or code fetches in 62-bit mode similar to 64-bit. No AR or unusable select checking for CSDs, ESFs or GS data or code fetches at any time. Restricted support for far call, far return, far jump, IRED or FRED. Did they manage call gate? Restricted subset of segmentation, so no gates are supported in the GDTL, DT, or it only supports data segments, no conforming code segments and TSS. Because this call gates, so I believe this also removes fully support for call gates, which, yeah, here maybe, is it another summary? Potentially this is another summary of, so a VMM can choose to emulate legacy functions as required. So VMM, of course, a virtual machine manager. So something like QEMU or Cloud Hypervisor and stuff. But truth be told, you normally wouldn't want to run this. This is more like running, like really running OS2 in VMware, Parallels, QEMU, VirtualBox and stuff. Because call gates are also a very rarely used feature. Maybe only, I don't know if Microsoft ever experimented with them or had support for something somewhere, but they were mainly used, as far as I know, in OS2, which of course somehow OS2 used all the craziest hardware feature, because why wouldn't you? And this is also why, fun fact, OS2 was one of the hardest to emulate and virtualize operating systems, because it made use of so many otherwise rarely used features. Call gates being a special mechanisms for code to call between different rings and segments. So normally you would, otherwise other operating systems only had a mechanism to use a space to system call into the kernel, initially with some interrupt, like interrupt 80 or stuff. And nowadays with the system call, instructions and call gates were basically a creative way of calling other code areas in other rings on other segments, like this or something of that sort. And so, like, yeah, as you see, it removes a lot of complexity. And this is why I previously said in previous live streams here, with going into details of x86, ISA and complexity, why I think Intel should remove that. I said this 1, 2, 3 years ago and for a longer time, and finally they do it, because as you see, even those features back in the day, like call gates and other such stuff, were only used by OS2 stuff, not even by mainstream Windows, let alone Linux. Linux is not even, I believe Linux 0 point something used hardware interrupt context switching, another crazy rare feature. I believe, as far as I remember, Linus Torvalds removed that probably before the Linux 1.0, but somewhere at that time, because it was found to be obviously less portable and maybe even less performant. That's like x86, so complex, hardware-assisted context switching, slower than doing it in software. As far as I remember, correct me if I'm wrong, but as far as I remember, doing it in software allowed more optimizations, like lazy context switching, FPU and other such stuff, or otherwise optimizing what to store and load and stuff. But correct me if I'm wrong, or otherwise it is removed in 64-bit long mode for a long time already. So yeah, that is basically the summary, a net 40-page plus surrounding stuff summary of what to remove in future processors. I hope they do it sooner than later. I would estimate that could give them maybe, of course I have not worked at Intel or AMD for that matter. I would, with my experience, guess it might save them maybe some 5% or something of that sort in this ballpark of silicon die error, at least in the decoder. Of course not all silicon die error, because the caches are so large and stuff, and TLBs and other buffers. So it could easily save them some 5% or so of decoder and other surrounding logic, and 5% is quite some, so potentially more clock. Like, I wouldn't be surprised if some of the stuff is rather timing critical and so on, decoding and handling and stuff, and certainly a lot of microcode. And because this kind of crazy features is not what you would implement in modern processors in hardwired logic, so it could potentially save them a lot of microcode space and a lot of surrounding bugs, quirks, and features, and yeah, more cores, higher frequencies, space for other features, maybe a 8-byte issue. I don't know if Intel has already 8-byte. I think the last time I looked, they had 6-byte issue decoder and stuff. So maybe 8-byte decoder, because this timing critical code passes potentially with all this legacy code is like, yeah, that certainly it's mighty complex. And maybe it even saves them more than 5%. Maybe the stuff, it's just a ballpark guess, right? Maybe the stuff is so. If you've ever worked at Intel, leave in the comments below if it saves 10 or 15% of legacy decoding logic. Anyway, amazing stuff. Certainly what Intel needs to do to, I just made recently a video what Intel and AMD need to do to stay competitive with ARM, especially Apple Silicon, but also other ARM vendors, and upcoming RISC-V. Yes, RISC-V is not yet as high performance, but it only takes so long for new startups to re-implement all this embarrassingly massive out-of-order speculating and single instruction multiple data in RISC-V for them to overtake x86 in maybe 10 years or so. So certainly some stuff, some simplification, some reducing, not to say reduced instruction set computing, right, is certainly in order to gain the next 18, 20, 25% of performance, IPC increase, more cores, and so on, better energy efficiency, the usual things you would expect from your next generation of Intel Core processors. I hope you enjoyed this summary and learned something. I have a couple of other videos of in-depth, complex Intel and AMD x86, but also ARM, RISC-V, PowerPC, and Spark. And if you're interested in this stuff, I work daily with all of them, supporting all those architectures, 30 plus, in our Linux distribution from ARM to Super H, and certainly will continue to make more detailed videos. And we also have a massive release update coming, so you probably want to share, like, and subscribe to hear more about all of these things in tech, also on my main channel, where we develop on various architectures every other day live here on YouTube. So let's take a quick look. Not too many comments today. Let's just a quick minute look. Awesome about time drops and legacy instructions. Other comments. End of crappy hobby OS. So what? That use BIOS heavily. No, totally not. Doing EFI directly is no issue, and we are writing a microkernel, right? Running a Linux distribution for 25 years was not enough, because Linux is as too complex as Intel CPUs in the meantime. So I'm dreaming of a highly reduced nano kernel anyway. So if this is something you want to see, then it's twice the reasons to share, like, and subscribe. And doing low-level code in UEFI is super easy if you want to get started. There are plenty of hobby EFI stub things and even latest memtech test. So if you want to start with something, you could just copy memtest 86 and hack the memory testing out of it and start with that. So totally not the end of crappy hobby OSs, but just focusing hobby OSs on latest and greatest epic thread ripping enthusiast silicon. If you try, you can install Win on modern computers. I think it makes totally sense to remove. Even if you can try, you can't install it, remove 16. Yeah, I wonder that it took them so long. As I said in the beginning of this talk here, I wonder that they didn't remove it at least with like A20 gate removal. They could, Intel, if they wanted. I mean, sure, you could not have booted DOS anymore, but I mean, honestly, after the remove the A20 gate, you would need to have A20 gate aware, or A20 not gate aware, A20 aware, free DOS or so, hack DOS stuff, and it's like, yeah, come on. I mean, if you had to run some DOS application in production in 2008, there was billions of other used computers on recycling centers or eBay anyway. So yeah, somewhere like basically a decade ago they should have removed it and just defined we come up in 32-bit mode or whatever, and yeah, that or even 64-bit, it doesn't even matter too much. At least get rid of legacy and boot up with flat, reset to whatever, maybe even reset to the same vector address, but in 32-bit flat protected mode or so on. It would not have been rocket science even back in the day. But yeah, Intel, the wheels, the gears at Intel are also spinning slowly, and they're also only cooking with water. NetBeastie toaster, right, but it breaks OS devs tutorials on how to boot loaders in assembly. Yeah, again, the tutorials for EFI are not that much longer, so, and you could, I mean, truth be told, most OS dev hobby people start with running in QEMU or PC emulator or similar such emulators anyway, so all the, I mean, again, native 64-bit code is not that difficult, if not even easier. Especially you don't need to learn about all this REALMODE, interrupt, BIOS and whatnot nonsense, and like basically have modern code calling normal C APIs. So it's, for a newcomer not knowing anything about x86 legacy stuff, maybe even easier. Yeah, x86 suck less. That's it for this video. I hope you enjoyed and learned something, and see you soon for the next tech.